Section: Introduction. In this section, we discuss the significant impact of large language models, LLMs, on deep learning, highlighting their diverse applications such as assisting in code generation, healthcare, and theorem proving. We typically train LLMs in two phases. First, we pre-train them on large datasets, and then we refine their behavior through a process called reinforcement learning from human feedback, RLHF. This refinement involves using a lot of human annotated data and can be broken down into supervised fine-tuning, reward modeling, and RL fine-tuning. Despite their effectiveness, LLMs can produce harmful content, including hate speech and misinformation, due to the presence of negative elements in their training data. We observe that social media often showcases methods to exploit LLMs, prompting them to generate inappropriate responses. The definition of what is harmful varies based on user preferences, making the alignment process case-specific. To enhance safety and reduce harmful outputs, we have implemented various alignment strategies, such as incorporating safe information during fine-tuning and conducting red teaming exercises with human experts. However, we still face a continuous challenge, as new alignment techniques are developed to counteract increasingly sophisticated methods of manipulating LLMs, known as jailbreaking. In our work, we propose a theoretical framework to analyze both the pre-training phase and the jailbreaking issue. We recognize that jailbreaking prompts often retain harmful concepts while altering other aspects. Our framework allows us to separate input prompts, enabling us to measure the potential strength of adversarial attacks. By treating the outputs of LLMs as longer text segments rather than individual tokens, we can better understand how these models reflect their training data and identify vulnerabilities. We summarize our contributions as follows. We provide a generalization bound for pre-training based on our framework, suggesting that high-performing models will likely exhibit behaviors found in their training data, including harmful actions. We extend our framework to address alignment in jailbreaking, demonstrating that even after safety measures, jailbreaking remains a risk because LLMs do not focus their outputs solely on safe responses. We also identify a significant limitation in the commonly used RL fine-tuning approach, which struggles to balance harmlessness and helpfulness. By addressing this, we aim to create safer models that are more resistant to jailbreaking while maintaining performance. The organization of our paper is as follows. We introduce our framework in one section, prove the generalization bound in another, analyze jailbreaking statistically in a subsequent section, and finally, we present our proposed E-RLHF objective and its effectiveness in enhancing LLM safety. A literature review is included in the appendix. Section Summary. In this section, we discuss the transformative impact of large language models, LLMs, in various fields and outline their training process, which includes pre-training and alignment through reinforcement learning from human feedback, RLHF. We highlight the challenges of harmful content generation and the ongoing struggle between alignment efforts and sophisticated jailbreaking attacks, proposing a theoretical framework to analyze these vulnerabilities and improve model safety while maintaining performance. Section: PAC Bayesian bound for pre-training LLMs on harmful data. In this section, we explore the PAC Bayesian bound for pre-training language models, LLMs, on harmful data. We apply PAC Bayesian theory to establish bounds on the generalization gap, which is the difference between a model's performance on training data and its expected performance on unseen data. Our first key finding is that a well-trained LM can exhibit harmful behavior if it was exposed to such behavior during training, even when prompted directly. We define a set of prompts generated independently from a distribution, which, along with explanations, forms our pre-training dataset. We denote the prior and posterior distributions over LMs before and after pre-training. For a given prompt, we assess the LM's generalization ability by measuring the total variation loss between the model's output distribution and the true distribution. In practice, pre-training involves minimizing the cross-entropy loss, which relates to optimizing the KL divergence between these distributions. We express our PAC Bayesian bound, which indicates that if pre-training effectively reduces the loss on the training data, the LM will likely perform well on real-world prompts. Importantly, if the harmful concept is defined as producing harmful explanations with high probability, we conclude that an LM trained on harmful data can generate such explanations. Next, we discuss the potential for adversaries to jailbreak an LM even after it has undergone alignment. Our proof draws from adversarial robustness, suggesting that the adversary's success depends on the volume of points that do not allow for adversarial examples. We assume that the alignment process does not significantly alter the LM's ability to produce meaningful explanations. We define the output distribution of the LM concerning harmful concepts and categorize it into harmful and safe zones. The goal of alignment is to push the output distribution into the safety zone, ensuring that the LM responds safely to harmful prompts. However, we recognize that adversaries can still find ways to extract harmful explanations. To quantify the likelihood of jailbreaking, we assume that the adversary can manipulate the output distribution within a limited range. We introduce the concept of epsilon expansion, which describes how close a distribution can be to the harmful zone. Our theorem states that if the induced distribution is not overly concentrated in a safe area, the model can be jailbroken with high probability. In summary, we find that the chances of an adversary successfully jailbreaking the LM increase with their ability to manipulate queries and the ratio of harmful to safe explanations. This highlights the challenges of achieving effective alignment, as a small safety zone is often insufficient to prevent harmful outputs. Section Summary. In this section, we present a packed Bayesian bound demonstrating that language models, LMs, trained on harmful data are likely to exhibit harmful behavior when prompted, as the generalization gap between empirical and population loss can lead to the model mimicking harmful outputs. We also prove that adversaries can successfully jailbreak these models even after alignment, highlighting the challenges in ensuring safety due to the inherent imbalance between harmful and safe explanations in the training data. Section E-RLHF, Improving Alignment by Expanding the Safety Zone. In this section, we discuss E-RLHF, which aims to enhance alignment by broadening the safety zone. We recall that, as mentioned in the previous section, the likelihood of jailbreaking increases when the harmful zone is larger than the safety zone. The sizes of these zones depend on their respective explanation sets, meaning that the size of the preference alignment dataset is vital for effective alignment. However, the human effort required to create such datasets limits their size. To address the jailbreaking issue practically, we explore ways to expand the safety zone, particularly through reinforcement learning with human feedback, RLHF. RLHF generally consists of three phases: supervised fine-tuning, preference sampling and reward learning, and RL optimization. We focus on a popular version of RLHF called Direct Preference Optimization, DPO, which allows us to learn directly from the preference dataset without needing a reward model first. DPO is more stable during training compared to other RLHF methods. For our work, we assume access to a supervised fine-tuned language model and a preference-aligned dataset containing text prompts and human-rated explanations. In the second phase of RLHF, we usually optimize a reward model based on these explanations. Our proposal specifically targets the third phase, where we train the preference-aligned model. The goal is to maximize the reward while ensuring the model does not stray too far from the supervised fine-tuned model. However, we argue that this regularization can be problematic, as it may keep harmful explanations in the model's output distribution. To counter this, we suggest using a prior designed to create a larger safety zone by modifying harmful prompts to include safe concepts. This can be done individually or by adding a general prefix to all harmful prompts, while leaving non-harmful prompts unchanged. We call our approach E-RLHF, which modifies the training objective to include a safety-transformed version of the harmful prompt. We emphasize that it is not necessary to use the same harmful prompts for both the reference and target models, as long as the substitute prompts yield reasonable outputs. We provide evidence of our modification's impact in the appendix. In our experiments, we utilize the Alignment Handbook codebase and tune a publicly available supervised fine-tuned model using a public dataset. We label harmful prompts with the help of GPT 3.5 Turbo and apply the safe prefix to generate safety-transformed prompts. Our experiments are conducted on NVIDIA Tesla V100 GPS with half-precision tuning. We present empirical evidence that our modification, eDPO, improves safety alignment across various tasks. Additionally, we ensure that E-RLHF does not compromise helpfulness, as both DPO and eDPO models perform better than the original supervised fine-tuned model. We also explore the effect of the safe prefix on performance, noting that while it influences results, it never leads to failure. We believe that optimizing safe prefixes could enhance our outcomes, which we plan to investigate in future work. Finally, we confirm that the improvements stem from using a safe prior for harmful prompts and show that eDPO can be combined with any system prompt to further enhance safety, potentially improving both safety and helpfulness simultaneously.